Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. On, and in this tutorial video we'll go through this June 2015 so Cambridge International A-Level paper 2. This is paper 22, basically paper 2 variant 2 for the various geographical locations around the world, taking these Cambridge International exams, contents of which are suitable for any 16 to 18 years old chemistry students all around the world. In this first question, we have this thing on atomic structure. So we know that the atoms are made out of three types of particles. Of course, one of them is protons, and you have also neutrons. Both of them are in the nucleus. We have this very, very much lighter particle that is going to be electron, which is around 2000 times lighter. So typically, I will just write 1 over 2000. It's around 2000 times lighter compared to protons and also neutrons. But this is a positive one species, meaning to say it's got a +1 charge, so it cannot be neutron. It has got to be proton, leaving the other particle being the neutron. So the protons and the neutrons, they are in the nucleus of an atom, and since they are the heavy ones, the number of protons and the number of neutrons would therefore give you the nucleon number, and that is also the same as mass number, having discounted the mass of electron, which is much lighter compared to the mass of protons and neutrons, which are equal, and which is why the ratio of their masses is going to be 1:1, since they both have the same mass, and electron is the one that's much lighter. The electrons are in the shell outside the nucleus. They are in the electron shells. Electron has a -1 relative charge, the opposite charge of protons, and the neutrons will be uncharged in the nucleus of an atom there. So just like that, you get the 3 marks to get for this question. In this next one, we have this idea of isotopes. So we know that definition of isotopes are commonly asked. Atoms, they are different atoms of the same element. They have the same number of protons, so that's why the identity is the same. Should be 12 there and 12 there, because the number at the bottom represents the atomic number or the proton number, and then this number on top there, that is not relative atomic mass, that is what you call mass number, or you will call that as nucleon number, which is the number of protons plus the number of neutrons in the nucleus of an atom. So each one has their own relative isotopic mass. So I did say that the mass of that particular isotope is a result of the individual masses of all of these things. So these are given to 0.0. Typically they are whole number, but you also have electrons. They are going to be very much lighter compared to protons and neutrons. By right, they will include the mass of electrons, but because they're so much lighter compared to the mass of the nucleons, the particles inside the nucleus of an atom, the protons and neutrons, that's why most of the time it's just a whole number, which is the sum of the number of protons and the sum of the number of neutrons there. So what is meant by this relative isotopic mass? The fact that it's to do with the isotope, it is not average. So a lot of students, they're confused between the definition for relative atomic mass, relative formula mass, as well as relative molecular mass. The other 3 are definition as stated in the syllabus, something that candidates should be able to do as well. Those involve average, but not for this isotopic mass. So it is the ratio, it's always a ratio. And this is not average mass, it's just the mass of an atom of the isotope, because it's referring to a particular isotope. I'm referring to an atom, that means 1 atom, and this is relative to 1/12, the mass of an atom of carbon-12 isotope. Okay, the 1/12 is essential. In fact, relative to blah blah blah, this thing here is common across all the other relative atomic, relative molecular, as well as relative formula mass definitions. Because I was comparing 1 atom, this is 1 atom there as well. Now this is a calculation level question. We are told the relative atomic mass, which is to do with the average mass of all the isotopes relative to 1/12 the mass of an atom. Carbon-12, the average mass comes down to 24.3. So the 24.3, we need to calculate the percentage abundance of the third and the last isotope of magnesium first. We are told that this one is 79.0% and this is 11.0%. Therefore, the percentage of the other isotope which we don't know what is the mass number yet, is going to be 100%. Take away the difference between the other two. So there's 79.0 plus 11.0. But I use a bracket because these are the total percentage that I have so far. So 79.0 plus 11.0, I get 90.0. That will give me 10.0%, just to be consistent with the number of decimal place, the number of significant figure. I keep it to 1 decimal place there. Having done that, this is an algebra question. So let the unknown mass number, which you still don't know what it is yet, be x. And I know it's 10%. So the AR, which is 24.3, is equal to something divided by 100%. On the top there, I started out from the mass number 24, 24.0 times 79.0. So 24.0 times 79.0. I add it together with the other isotope, 26.0 and 11.0. So 26.0 and 11.0. And then I have to do the unknown mass number, which is x, and then that is multiplied by 10.0. Better improve my handwriting a little bit. So there's 24.0. So altogether now, I can just multiply the whole thing on the top. I'm going to move up the 100 to the other side. Divided by 100, move to the other side, become multiplied by 100. So 24.3 multiplied by 100, that is 2430. So multiply the numbers that you can multiply. So 24.0 times 79.0 plus 26.0 times 11.0. I get 2182. And then the algebra on the other side is x times 10. So I just get 10x. So 10x equal to, I move the 2182 to the other side. And I have just swapped the number around. Okay. And then what I get is 10x equal to 2430 minus 2182. So there's 248. So what is x then? X is going to be 248 divided by 10. X is 24.8. They want me to give my final answer to 3 significant figure. 1, 2, and 3 significant figure. It gives me an exact answer, 24.8 there, to 3 significant figure as well. So that's it really for that 3 marks. The next question, we have some electrolysis of magnesium chloride. Now this is part of the 2015 syllabus. It's one of the last syllabus before the introduction of that new syllabus from 2016 onwards. And now from 2022 onwards, there is a new syllabus again. So electrolysis of these kind of ionic compounds have been phased out from the AS chemistry. So if I were you, I would really go through my curriculum, objective, my syllabus, so that I know exactly what is and what is not in the syllabus. I'm still going to show it anyway because it's quite a cool question to ask. This is straight from your IGCSE or GCSE or O-level chemistry. But just so you know, electrolysis are still in the A2 electrochemistry topic. So you could be asked this in A2 instead. We know that at the cathode, reduction happened. So red cat there stands for reduction happened at cathode. We know that reduction involves gaining electrons. So reduction is gaining electron. So I will gain electrons at the cathode. And cations go to cathode. So cations is positively charged. So therefore cathode is negatively charged. So my cations, this is a molten compound. So I just have Mg2 plus and Cl minus. Cl minus is my anion. It goes to the anode because the anode is going to be positively charged. And that is why the anion, which is negatively charged, goes to the anode. So Cl minus go to the anode, Mg2 plus go to the cathode. Reduction happen at the cathode. I gain electrons and I get my magnesium. So the Cl minus will give me Cl2 and I will lose electrons because oxidation happen at the anode since reduction happen at the cathode. Whatever equation you write have to be balanced. So there's 2 electrons there to balance out the charges, 2 Cl minus there, and 2 electrons that you have lost from the 2 Cl minus. Okay, balance equations, half equations, 2 marks, showing reduction, gain of electron, showing oxidation, loss of electrons by having these plus 2 electrons on the right hand side there. This next question is really an AS level question, still in the syllabus because it is simply about empirical formula. So what do we have? We have magnesium, we have oxygen, we have hydrogen and chlorine. So we're told that these are percentage composition by mass. As you know, percentage is out of 100%. So these are going to be the 21.65 gram. If I have 100 gram of this substance, the percentage by mass is out of 100% is going to be the mass out of 100 gram. So that's 31.65 gram, 20.84 gram, 1.31 gram, and 46.20 gram. And this will give me a total of 100 gram since it's out of 100%. But I just want the mass over AR because empirical formula, AS level definition, it is the simplest whole number ratio of the atoms. So these things are not molecules, they are going to be atoms. That is why we use the relative atomic mass straight from the periodic table there. So this one is going to be divided by 24.0. Oops, hang on. I think it's 24.1 in the periodic table. You gotta be careful and use the periodic table that you are given in the A-level exam paper. So not just any periodic table. So yeah, it is 24.3, not 24.1. In fact, it was already provided in the previous question, 24.3 there. So I was mistaken there. So the oxygen is 16.0, the hydrogen is divided by 1.0, the chlorine is divided by 35.5. So mole equal to mass over AR. So we're trying to find the simplest whole number ratio of the atoms. So this gives me 1.30. 20.84 divided by 16.0, I get 1.30 as well. And this one divided by 1.0 is 1.31. Last but not least, I get 1.30. So you don't just round it up to 1. Instead, you have to divide by the simplest number or smallest number to get the simplest ratio. So you divide by the smallest number in order to get the simplest ratio. The smallest number is going to be 1.30. So I'm just simply showing that 1.30 divided by 1.30 is just 1. So this is 1.31 divided by 1.30. It's not exactly equal to 1, but it's very, very close to 1. So I'm just going to round it up to 1. And when it asks you to show something, you don't stop here and round it up. Instead, you need to divide by the smallest number to get the simplest ratio. A lot of students, when they do any sort of formulas or calculations, they're like, I know how to do it, but I don't know how to explain it. So that means all this while you're probably just learning like things, you know, by memorizing instead of knowing where things come from, and that is a big danger on its own. So there's going to be Mg, O, and then H, and then Cl. This is empirical formula, simplest whole number ratio of the atoms. So I'm just going to write it in that space there. Now part D. Part D is about acid-base behavior of the oxides in the third period. This is a continuation of acidic, basic, and phosphoric oxides from your O-level, GCSE or IGCSE level days. So describe this behavior and explain it. So you got to describe as well as explain it to the structure and bonding of sodium oxide, aluminium oxide, and then sulfur trioxide. So we know from the left to right, so from sodium to aluminium to sulfur, so left to right across the period or across period 3, metallic character decreases. Metallic character of the element, metallic character of the element decreases, and it becomes non-metallic, i.e. sulfur is non-metallic. Sulfur. So what we can see is we have these graduations where we have electronegativity. Oxygen is there, one of the most electronegative elements. Only fluorine is more electronegative than itself. Fluorine, oxygen, nitrogen, very electronegative. Then what I have there is going to be sulfur. Then I will have aluminium and then sodium. As you could see, sodium and oxygen, biggest difference in electronegativity. And then sodium, what am I talking about? Aluminium and oxygen, slightly smaller electronegativity difference, and then sulfur and oxygen, even smaller electronegativity difference. So my first point was that. My second point is that, therefore, sodium, from sodium to aluminium to sulfur, smaller difference in electronegativity. Smaller difference in electronegativity. with oxygen, so comparing to oxygen. So therefore, what can I say? Bonding shift from ionic in Na2O, Al2O3 to covalent in SO3. So I haven't even been able to describe the behavior yet. I should probably try to describe the behavior, right? So metallic character decreases. Maybe I can say, I'm trying to save some space here. It's quite important to actually be able to plan your answer properly, right? So those are metals. They form, well, I know that they are metals. So Na2O is basic oxide. But then Al2O3 is quite your special one. It is your amphoteric oxide. It will react with both acid and bases. But then what else can I say about sulfur? So sulfur is non-metal. So SO3 is acidic oxide. I guess that's probably the best I could think about in terms of my second point. Well, my first point there. In terms of the behavior, I talk about the basic oxide. I talk about the amphoteric oxide. I talk about the acidic oxide. I also talk about the smaller difference electronegativity in terms of the bonding shifting from ionic to become covalent when it eventually reaches to SO3 there. Phew, okay, never mind. We're going to write equations now. There are 4 marks for here. You see the 3 oxides with hydrochloric acid and or sodium hydroxide as appropriate. So first of all, we know that we have to write one equation for the basic oxide reacting with acid, sort of like Na2O, reacting with HCl. These are basic oxide reacting with acid. It's going to give you the salt and water neutralization reactions. Any equation you write needs to be balanced. So 2 Na there, so 2 NaCl, 2 chlorine there, so you need 2 HCl, and then 2 hydrogen and 1 oxygen, 1 of that water. So no problem there. Now onto the basic oxide, onto the acidic oxide SO3, and that will react with sodium hydroxide. So this is SO3. SO3 is sulfur plus 6. So they will give you the salt which contain SO42-. This is also sulfate. This is sulfur plus 6 oxidation number. Leave you to do the exercise on your own to work out the oxidation number of sulfur when the oxygen is -2 oxidation number there. So your salt is going to be sodium sulfate, Na plus SO42-. You need 2 of the Na plus, and then you will get water. Similarly, you have to balance the equation, 2 sodium there, so 2 NaOH, and 1 of that sulfate, meaning 1 of that SO3. SO3 plus another oxygen, SO4 there, and then the other oxygen goes here, the 2 hydrogen goes there, water. That equation is balanced now. Now with the Al2O3, because it's amphoteric oxide, it reacts with both acids and also bases. You've got to show 2 equations. One, where the Al2O3 reacts with acid, so that means the Al2O3 is acting as a base, it reacts with acid. The salt you're going to get is Al3 plus Cl minus AlCl3. But in fact, we know that this is a bit covalent. Think about your Al2Cl6 under the dative covalent or coordinate bonding as part of the covalent bonding case study molecule. And then this one will produce water. I have 2 aluminium there, so I need to have 2 aluminium there. I now have 6 chlorine. I need 6 HCl. And now I have 6 hydrogen atoms. I need 3 of that water molecule. Last but not least, this is probably one of the hardest one to do for a lot of students because you need a bit of skill to do this one properly. Okay, so what I know is that when you have Al3 plus aqueous, you know that it will react with hydroxide. This is the test for aluminium ion in your paper 3 qualitative analysis ever since your GCSE, IGCSE or O-level days. Whether you've done this practical or not, you must know about the theory as well. You get a white precipitate. Now that is when Al3 plus is added to a small amount of hydroxide. So you get a white precipitate forming. And then after that, you know about this white precipitate, it will dissolve in excess NaOH. So I add in more OH minus aqueous. What's going to happen is the solid, the white precipitate, will dissolve. And what do I get? I get this complex. So instead of 3 hydroxide, I now have 4 hydroxide. I have aluminium 3 plus and then 4 of that OH minus. So this is going to be minus, and Na plus is an ionic compound, is aqueous. That is why the stat symbol there is aqueous, because that thing is soluble. This thing is colorless in solution. So what you get is the precipitate dissolve to give you a colorless solution. So there's a solid dissolving excess sodium hydroxide to give you this colorless solution. Similarly, this is actually one of the possible formula of what you could actually get. What you will get is Na, and then I always write as Na plus and then Al, bracket OH, 4 of it, and then minus. And then I know that this is going to be aqueous, but then when you look at balancing the equation, you have 2 aluminium on the left-hand side, so I need 2 of that aluminium on the right-hand side. Having done that, I've got 2 sodium, so I need 2 NaOH. Having done that, you will see that I've got 4 oxygen and 4 hydrogen, but I've got 2 multiple of it, so I got 8 oxygen and 8 hydrogen. I've only got 3 oxygen plus another 2 oxygen is 5 oxygen. I'm still 3 oxygen short, and usually in this kind of equation, you just add water. Usually our water is on the right, but here it's impossible to put more H2O on the right because the equation will not be balanced. So instead I put the H2O here. Like I said, 8 hydrogen and 8 oxygen if you do the multiple correctly. So you already got 2 hydrogen. I just need 6 more hydrogen. I put a 3 in front. Now let's check the oxygen. 3 oxygen plus 2 oxygen is 5 oxygen, plus another 3 oxygen, you get 8 oxygen, and you have 8 hydrogen. That matches this soluble complex, we call it. Okay, so this product on the right hand side is basically this colorless solution, the active ions present in this colorless solution as the white precipitate dissolve in excess NaOH. That's the end of that 80 mark inorganic chemistry question there. Question number 2, we have sulfuric acid. So we know that it's manufactured by contact process, one of the very important reactions involving at least, only one of the steps is actually reversible, and that happened to be a very popular equilibria question as part of physical chemistry. Anyway, what do they want us to do here? They want us to write an equation for the reaction between galena. So galena is actually PBS according to this question. So this thing is reacting with oxygen. So oxygen in the air, oxygen molecule, I guess. And then you're going to form sulfur dioxide. Di there refers to times 2 oxygen. And you're going to get lead 2 oxide, where you have Pb2 plus and O2 minus. As you can see, the charges cancel out. You just need 1 of each there. So it's PbO, lead 2 oxide, because you can also have lead 4 oxide, where you have Pb4 plus, and the formula will be PbO2. Well, balancing the equations, you will see straight away that this equation is not balanced because 2 oxygen plus 1 oxygen is 3 oxygen. You have 3 oxygen atoms there. You need 3 oxygen atoms. Start to use fraction. So 3 over 2 is the best one to use because 3 over 2 times 2, 2 oxygen in 1 molecule, 3 over 2 fraction in front, you get 3 oxygen atoms on the left-hand side. However, some people really don't want to use fractions, despite having done fractions in chemical energetics as part of AS level physical chemistry. You know that the use of fractions is acceptable because, it is after all a symbolic representation. That's what chemical equation is all over. So you could multiply by 2, you could get 2, 3, 2, and 2. They will also be balanced. It's just 2 times multiple. Anyway, the next bit, identify oxidation number, but be careful, they want the changes. Changes means from something to something. So make sure you specify that. Okay, we know we started from lead 2. We need to work out lead 2 oxide formation from lead 2 sulfide. So this thing is called lead 2 sulfide. IDE because it's S2 minus, Pb2 plus, S2 minus. So we can see that there is no change in the oxidation number of the lead there at all. But we know that oxygen from 0 in O2 to minus 2 in SO2 and also PbO. So the change there is from this to this, or you can say -2 -0, the change is -2 there. In terms of the sulfur, is there any changes in the sulfur? There are no changes in the sulfur as, oh, there is a change in the sulfur. There is a change in the sulfur. So we know it's Pb2 plus S2 minus. So that is from -2 in PbS. Your ionic compound contains the S2 minus. The oxidation number of the species is the charge of the ion. So it's -2 in PbS. Now you have SO2. SO2, the sulfur is bonded to something more electronegative than itself. So you got 2 oxygens. The oxygen is going to be the one that carry the -2 there, because the oxygen is more electronegative than sulfur. Electronegativity, AS level concept, the ability or the power of that atom to attract the bonding electrons toward itself, leaving the sulfur with a positive oxidation number. Overall, the oxidation number of this compound, of this molecule, is 0, and that is part of the rules of oxidation number there. So it goes to +4 in SO2. The oxygen, so this is referring to the oxygen, so that's why it's -2 in SO2, but the sulfur is +4 in SO2 there. So the change is going to be +4 minus -2. If you think about it, +4 is the final one, -2, that is +4 +2. You get an increase of 6 oxidation number. Okay, hopefully that makes sense to you. Now the next bit is basically about this equilibria. As I did mention, there is one step in the contact process. Somewhere along the way, to produce your H2SO4 sulfuric acid, you need to go through this main-mate equilibria process, reversible reaction there. So state the temperature usually chosen. So typically it's around 400 degrees Celsius or 500 degrees Celsius. Around 400 to 500 would be alright. If you want to be safe, you can write 450, but I think 400, 500 degrees Celsius will have been alright as well. But they did say the temperature, so you shouldn't give a temperature range. You shouldn't give 400 to 500 degrees Celsius, but really, I mean, they would have been acceptable as well. I imagine that. Now explain this in terms of reaction rate and also Le Chatelier principle. Le Chatelier principle basically says that when a system is in equilibrium and you introduce a change to the system in equilibrium, the equilibrium will try to oppose the change in order to go back to equilibrium. So it's basically like push and pull. It's basically like homeostasis in biology. It's basically yin and yang, just like in physics, you know, forces, push and pull, that kind of stuff, reaction and action forces, Newton's third law. Reaction rate is how fast. How fast is the reaction going? Le Chatelier principle is to do with equilibrium, is to do with how much. How fast versus how much is often something that is asked in this idea called rate versus equilibrium, and it happens to be one of those things that always asked together because students always get them confused, and examiners love to ask this again and again and again. You get 1 mark here in terms of this temperature. So high temperature is required. In fact, high temperature favors faster rate of reactions. It will make the reaction rate faster or higher. Reaction rate higher or faster. They did say explain, right? So you got to talk about Le Chatelier principle. Boltzmann distribution. What am I talking about? Okay, so molecules or particles. Molecules will have greater kinetic energy, and your whole Boltzmann distribution would actually shift to the right-hand side, and therefore there are greater proportion of molecules with enough energy greater than or equal to EA, therefore rate is higher. Okay, so in terms of the equilibrium, so however, the forward reaction is exothermic. If you look at the enthalpy change, is negative there. So the forward reaction is exothermic. We're going to talk about Le Chatelier principle. As temperature increases, the equilibrium or the system which is the equilibrium, so it doesn't matter, you want to use equilibrium or the system, will try to oppose the change. It will try to decrease temperature. All right, so how would you decrease the temperature all you know is you just know how to release heat. And that's why we stated the first statement, the Ford reaction is exothermic, it releases heat. When we increase temperature, the system wants to try to oppose it to decrease the temperature. So you will still release heat because that's all you know, but you will release less heat. And when you release less heat, you're going to favor the backward side, because when you favor the forward reaction, it will release more heat. Those to release less heat, you will favor to the left-hand side. So therefore, equilibrium shift to the left and explain blah blah blah, and therefore it will favor backward reaction. So in terms of the yield of SO3 will decrease. So we get lesser SO3 in this equilibrium as temperature increases. So really 450 degrees Celsius is really a compromise between you wanting a low temperature versus the reaction not going too slow. So this is a compromise temperature where the equilibrium yield of SO3 is acceptable enough at this high temperature, given that the rate is not too slow, such that you have a productive day in the industry, not having to wait for your products for such a long time. Anyway, the next question really is about stating and explaining as well in terms of the pressure conditions. Now, in terms of these conditions, why these conditions are not actually used. So from your syllabus, you will know that we use 1 atmospheric pressure. So unlike the Haber process, where you actually have to go to like 200 or 300 atmospheric pressure to have an appreciable equilibrium yield of that ammonia, here 1 atmospheric pressure, you already get good enough yield of SO3. So despite the 3 moles of gases, 2 mole of gas plus 1 mole of gas, 3 moles of gas on the left and 2 moles of gas on the right, despite the 1 atmospheric pressure, it is good enough to actually produce a high enough yield of SO3. So we apply and use 1 atmospheric pressure. That is your condition. So in terms of rate, so higher pressure is good, because higher pressure means the reacting particles or the reacting molecules are squeezed much closer together, and therefore in terms of collision frequency, they will collide more frequently, and when they collide more frequently, the rate is faster, so the rate of reaction is faster. Okay, however, in terms of equilibrium, it's basically Le Chatelier principle again. So we count the total number of moles of gases. We have to look only at the gases on the left and on the right. 2 mole of gas plus 1 mole of gas, so 3 moles of gases. So a lot of students, they just know like, oh, they state 3 moles on the left and then 2 mole on the right. Should be 3 moles of gases on the left, 2 moles of gases on the right. So you think about, the greater the number of moles of gases, the greater is the pressure exerted. So when you increase pressure, when pressure increases, the first thing the system will try and do is to oppose the change. So therefore, the system will try to oppose the change. The system tries to decrease pressure. And how do you decrease pressure? You want to shift to the side with lesser gaseous molecules, and therefore you will shift to the right-hand side, because the right side has lesser number of gaseous molecules. That was what we had stated previously. And given that higher pressure will give you faster rate, higher pressure will give you a greater equilibrium yield because you shift it to the right-hand side. But why do we not actually use higher pressure than 1 atmospheric pressure when we do use 200 atmospheric pressure for Haber process? That is because even at 1 atmospheric pressure, which is what we use, the yield of SO3 is already acceptable and quite high. So it is actually the cost factor. It costs a lot more to go to higher pressure So the yield is already acceptable, and it's expensive. It's expensive. So it's acceptable, it's already quite high. It is expensive to apply even higher pressure. When you already have good enough yield, you might as well, stick with it and be happy with it. Whereas in the Haber process, you really don't have an acceptable yield of NH3, and therefore you have to really increase the pressure to a much higher pressure. There's 200 atmospheric pressure for Haber process to produce ammonia. I think I've written more than enough there. In the third stage of the process, the sulfur dioxide is dissolved in this 98% sulfuric acid. So what you actually get is you get oleum. If you think about the equations, so the SO3 actually dissolve in concentrated sulfuric acid, and then you add them up, you get H2, S2, or 7. That is what you call oleum. And then this H2, S2, or 7 is what you dissolve in water to give you your concentrated sulfuric acid. And when you balance the equations, you will need 2 of that. So 4 hydrogen, 2 sulfur, and then 8 oxygen like that. So why in the world did we not just do it directly? Because we know that in the formation of acid rain is basically your rainwater. Your rainwater is H2O, and that SO3 that was produced by these catalyzed oxidations of SO2 reacting with NO2, giving you SO3 and NO again. Of course, the role of the NO2 is acting as a catalyst there, as the NO initially would have been produced, the NO2 would have been produced from NO oxidized by the oxygen in the air to give you NO2. This is what happened in the formation of acid rains. This is the catalytic cycle, giving you the SO3, not in a reversible step, because you are in the atmospheric chemistry region. Okay, so that's H2SO4, and that is your acid rain. So you will see that in the formation of acid rain, this is directly done. But then in industry, this is man-made process. This is natural atmospheric formation of acid rain. We don't add the SO3 into water straight away in industry because it's actually very, very exothermic. So we are dealing with human life in industry. So in terms of chemical engineering aspects, when something is very, very exothermic, it releases a lot of heat, as well as and also corrosive H2SO4 fumes. So it is safer to go through via this oleum route, which is less exothermic, and therefore you maintain the safety inside that industrial process there. So write equations for the reaction of sulfur trioxide with sulfuric acid and for the subsequent reaction. So basically this is via the oleum. You don't really need to know the formula of oleum because you know that based on what I've done earlier. So oleum is basically you just sum up the whole thing, 2 hydrogen, 2 sulfur, and 7 oxygen, and from there you can just add water to give you your sulfuric acid there. I've just added in the name oleum so that it sounds fancy, but it's actually part of your syllabus content even when you are doing the GCSE, IGCSE, and O-level chemistry. Okay, so it had equations, so you're supposed to have 2 equations showing you the stepwise formation of the H2SO4 from SO3, not from the acid rain, but in the man-made process here. Whereas this was direct route because this is in the atmospheric chemistry, the formation of acid rain, the H2SO4 in acid rain there. Now this this part D question, this thing has been taken out from the syllabus if I'm not mistaken. So we use it as additive in some food and wines because this SO2 prevents, so it's an antioxidant. So it's an antioxidant. It prevents your food from getting oxidized. So it prevents food from being oxidized and going bad, rotting, okay, due to the oxygen in the air there. But if I'm not mistaken, this has already been phased out from the new syllabus, so you will no longer see it. But if you go back to like the 2015 Cambridge International Syllabus, you will have seen this particular statement and how it is being used as additive in foods and wine. Now question part E, we have a calculation, a mole calculation question here. So the wine contains SO2. As it was mentioned, you add it as an additive in order to prevent the wine from getting oxidized, because wine has alcohol, and when the alcohol gets oxidized to carboxylic acid, your wine will no longer be having the alcohol content. It will just be sour, and you don't want to be drinking sour wine. Otherwise, you just be, you might as well just drink some vinegar, okay, like a apple cider vinegar or something like that. Anyway, how many moles of SO2 are present in 50 cm³ of the wine? So what do we have here? We are given information on the iodine, and the iodine will react with the SO2 in the wine. We want to know the mole of SO2 present in the wine. So we reacted 50 cm³ of the wine, which is the whole of that. So we find the information on the I2. We can see that the mole of the SO2 is to the mole of the I2. 1 mole of SO2 reacted with 1 mole of I2. Oops, sorry, not 2 at the bottom, but 1 at the bottom. 1 mole of SO2 reacted with 1 mole of I2 from the balance equation. You will know that I like this fraction method, as I have done in all my topical playlists, in all the topical structure questions, topical multiple choice questions, in all my previous tutorials. I've done this fraction method. Then on the right hand side is my actual amount. I want the actual amount of the mole of SO2. At the bottom, I have the concentration, which is in mole per dm³. So N equal to CV. But the most common mistake really is people forget that cm³ have to be converted to dm³ in order for the unit to cancel out. So at the bottom, I have 0.010 mole per dm³. That's 12.35 times 10 to the minus 3, or divide by 1000. I just move that up there, and I get the actual mole of the SO2 that's present in the wine. So 0.010 times 12.35 times 10 to the minus 3, I get 1.235 times 10 to the power minus 4 mole. Looking at the option here, I have 1, 2, 3, and 4 significant figure. This is 2 significant figure. This is 3 significant figure. This is 4 sig fig. I would say 3 to 4 sig fig. 3 to 4 sig fig would have been acceptable in this question. I'll just leave it as the exact answer here, because this is 4 sig fig within the range of these 12.35 cm³ there. So how many moles of SO2 are present in 1 dm³ of the wine? So if we have 50.0 cm³ of the wine, and it has this much SO2 dissolved in it, so therefore if we have 1 dm³, which is 1000 cm³, so I cannot compare 1 dm³ straight away because the units are not the same. Now that the units are the same, I can do my direct proportion, because if you do the direct proportion correctly, the unit volume will cancel out. So 1000 cm³ divided by 50.0 cm³, and if you can follow the math and follow the unit, you will see the cm³ and the cm³ cancel. So that is a factor of 1000 divided by 50, so I get 2.47 times 10 to the power minus 3 mole. Let me just double check my calculation, because I might have pressed it incorrectly just now. Yep, I get 2.47 times 10 to the power minus 3 mole. What's the next thing they want to sum up this question? They want how many milligrams of the SO2. Typically, we work in gram because mass over mR is in gram over gram per mole. What do they want? In the 1 dm³ of the wine. Give your answer to 3 significant figure. So basically they want the mass, okay? Without thinking about gram or milligram, they want the mass. They want the mass of SO2. So I have the mole of SO2. I want the mass. So realistically speaking, I need the mR of the SO2, and this is going to be 32.1 plus 16.0 times 2 from your periodic table. And I get 64.1 there. So what did I want? They want in 1 dm³ of the wine. So we know in 1 dm³ of the wine, there was this much mole. So if we have mole equal to mass over mR, so the mass will be in gram, you see, because the mR is, what is the mass in gram for 1 mole of the substance? So the mass there is going to be the mole times mR. So the mole is 2.47 times 10 to the power minus 3 mole. I multiply that by 64.1 gram per mole. The gram per mole and the mole will definitely cancel out. My point is your mass is in gram. So your previous answer times by 64.1 and I get 0.158327. This is in gram, but they want it in milligram. They even stated the answer here in milligram, and one gram is 1000 milligram. So I simply multiply that by 1000 milligram, and this is present in 1 gram. So the per gram and the gram cancel. Basically, I just need to multiply by 1000, and I get 158.327. This is now milligram. But again, they want it to 3 significant figure. So 1, 2, 3. I look at the fourth one, and this run up to 158 milligram of this sulfur dioxide in this 1 dmq of wine there. So that's it really for this 18 mark. Really good question here. Question number 3, we have ethane reacting with chlorine to form chloroethane. This is very clearly a free radical substitution reaction because you are dealing with an alkane chemistry. So alkane contains only carbon-carbon and also carbon-hydrogen bond. These are strong bonds. They are considered non-polar, so you're not going to be attacked by a nucleophile. Neither do you have double bond that can attack electrophiles. So the only thing you can go through is substitution, and you're going to substitute out with free radical. That's why it's called free radical substitution mechanism, as you have learned this as your AS case study mechanism. Of course, as with any of the A-level chemistry mechanism, feel free to browse through my topical playlist on the A-level concept videos. Under organic chemistry, there are all the 5 mechanisms, each of which I outlined in a separate tutorial video with example of my choice. And of course, you need to practice drawing it out for yourself with an example of your choice as well. Now use bond energies in order to calculate the enthalpy change for this reaction. You will do well to notice that all of these are in the gaseous state. That means we can use bond energy. We know that our bond energy in the use of calculation for enthalpy change is going to be the bond energy broken. So there's the reactant side, and I need to have minus the sum of the bond energy formed on the product side. So I break this thing and I form this thing. Now you could also be thinking about this in a simpler sense, because I do not really want to break everything, because I can, but then it will be a waste of time. If I purposely draw this as a display formula, then you can see hopefully that we are not actually breaking everything, because we can do much better than that. We can see that, let's say this blue color one, I am breaking that and I'm breaking that. I break that and I break that. Why? Because now the CH becomes CCl. So technically speaking, I am forming the CCl and then I'm forming the HCl. So I just need to break one of the CH, one of the ClCl, one of the CCl, and one of the HCl. These two are being formed, these two are being broken. So going straight to my data booklet, so find the bond energy. In the new syllabus, in the new specification for your exams, you will have the data inside the question paper itself. So, it wouldn't make too much of a difference. You still have a data to do your calculations where the question is needed. So find the CH first. That is given as 410. So 1 times 410 plus breaking the 1 times ClCl. That thing is 242, and then use bracket very wisely, close them up, and then minus the sum of the bond energy formed. You're forming one of that CCl. The CCl is 340, so 1 times 340, and then you have one of the HCl. So the HCl bond energy is 431. So I'm going to sum up this side. So 410 plus 242, that is 652, and then minus the other side, 340 plus 431, that is 771. So press that to your calculator. Do not forget the enthalpy change has a sign, has a value, and has a unit. The problem with the sign is when it is positive, your calculator will not show you, so you need to keep your eyes out for enthalpy change, having sign, value, and also unit. So this is minus 119 kilojoule per mole. Now for that 3 marks, some students will have been taught that you need to break everything, including all the CC single bond and the CH one. And here you are forming the CC single bond and 5 of this CH again. So you just be wasting time in these sort of questions. Free radical substitution, where you just substitute one thing here. You don't really need to break everything. There are cases where you do need to break everything that you see, such as combustion. So combustion of alkane, for instance, you get carbon dioxide. That means you must have break every single thing in here. Those are one of the few cases where you do really need to break everything. Okay. Now state the conditions for this reaction to occur. As I mentioned, it was a free radical substitution reaction. So you need your ultraviolet light. So ultraviolet, abbreviated as UV light. And what else? State the conditions needed. That's all really. Okay, so the UV light is essential for these reactions. What we have is this chloroethane to carbon hydrogen alkane, chloroethane, being formed from ethane molecule. And we're going to use a series of equations. This is a 5-mark mechanism. Now you're going to have an indication of how butane can be produced as a minor byproduct. This will be in your termination steps. So my first step is what I would call initiation. Initiation is basically the homolytic fission. So this is the homolytic because it's the equal breaking of the covalent bonds such that you get Cl like that, half-headed arrow. They call it a fish hook arrow, half-headed because one electron goes here, one electron goes there, and you get Cl dot. This is called a chlorine free radicals. So homolytic fission, equal breaking of these covalent bond such that the bonding electrons are shared equally or are split equally. Homolytic fission of the Cl2 to give or to form chlorine radical. So this is called radicals, free radical, species with an unpaired electron like that. The next step would be your beginning of propagation. You must show at least 2 propagation steps. So let me start with CH3. Then I add it with Cl dot. That is going to give me CH3, CH2 dot on the carbon. And now the Cl dot will have formed the HCl by taking away one of the hydrogen. But then I have not shown the formation of chloroethane from my propagation. So I need to show the formation of my desired product in my propagation step. Having done that, I also generate another chlorine radical, and this chlorine radical can attack more of the original ethane, and it's like a cyclic loop kind of thing. That is why it's called a chain reaction, because it just keep on reacting without much control, to be honest. Now, in terms of the last step, it's called termination. Termination is basically radicals recombine. So you will see that in the propagation step, you will have a 1 radical on the left. So no radical plus radical, giving you radical and no radical. You have 1 radical on the left and you have 1 radical on the right. That is the signature of propagation, radical forming radical. Termination is the opposite of initiation. While initiation requires UV light, that means you have high activation energy. Termination is one step with lowest activation energy because the radicals recombined to give molecule. So molecule is not species with unpaired electron, they are just molecule because the radicals recombine. So example, you want butane to be produced as a minor product. So I will get CH3, CH2 dot. So usually I will show the formation of this in the termination step. However, they want the formation of butane as a minor byproduct. So I just have another of this radical and radical. They can combine to give you CH3, CH2, CH2, CH3. This is the butane minor byproduct because your intention really is to show the termination step forming the desired halogenal alkane. Let me see if I can move this up here. So there's your propagation step, and I'll have one more line which I can write my termination there, and they will look a bit neater, I hope. I think. Where does that come from? There's give. Nope, that doesn't look so well. Just give me a minute. All right, okay, that looks better. Of course, I can write another termination step. So the CH3CH2, usually I will use it to form the desired product as well. So you can see that there is a similarity between this termination step to form this product versus this propagation step to form this product, in the sense that we get the product formation, but in two different steps. Here is radicals and radicals recombined. I don't get any radical on the right side, but here I get radical on the left, I get radical on the right side as well. In this next question, we have chloroethane. This is one question where I'm going to draw some skeletal formula: CH3CH2Cl, C2H5Cl, and then I get this ethane. This is ethane molecule. I have chloroethane on the far left. Now what do I have here? So what am I going to do? Chloroethane can be converted via an intermediate compound. So I guess I could convert it via this. And then I could reduce that. So I could eliminate that. So if I go from here to here, this will be elimination of your HCl by using NaOH in ethanol. And then from this alkene, I can then go back to the alkane. This is addition of hydrogen, or what I should normally call it will be reduction, where you reduce, where this above the carbon, gain hydrogen. Catalytic hydrogenation is the name of the reaction, but the type of reaction is undoubtedly called reduction there. Any other way you can do this? There could be another way. There will be Cl, and then you could get OH, and then you could get like that. No, but that is not the alkane, that is the alkene, because here I have done substitution. This is hydrolysis or substitution, and this one is done in NaOH, aqueous, so that means it's not in ethanol, and then you have to reflux that, and then you minus H2O, that is your elimination of H2O, and they'll give you back your alkenes, and then only then you can get the alkane by doing H2 and nickel catalyst. There will be your reduction step there. So there will be a reduction, but you can see that that is more than one step. There's 1, 2, and 3 steps. Here is just 1 and 2 steps, and this is as stated in the question, so I can't really do it via this thing first. I just have to eliminate the HCl, and then I do a catalytic hydrogenation, but the type of reaction is reduction, or you call it addition of hydrogen. That's perfectly fine. So the name of X there would be what you call ethene, a 2-carbon molecule, 2-carbon alkene. They want the name, they don't want the formula. They want the reagent and condition for reaction 1. This is the elimination of hydrogen halide. So you are trying to remove HCl from your halogen alkane to give you better alkene. You also use NaOH, but here you will see that this is substitution, this is elimination. Substitution versus elimination from the halogen alkane is a very, very important concept that get asked time and time again. You can watch my topical playlist under halogen-alkane structured question. There are a bunch of questions that I chose to highlight for the substitution versus elimination kind of case study over the years, and hopefully that will be useful to you and other learners, your friends and juniors and seniors. So do share those playlists with other people as well. They're entirely free for everyone to watch. So here, the NaOH in ethanol, and you also have to reflux it as well. So now suggest the reagent and conditions needed for this reduction. So we need the H2 as your reactant. Let me write that better. And you also need the nickel catalyst. And you do these at not reflux, because these are gaseous reactions. This is a solid catalyst in a different phase from this gaseous reactant. This is a heterogeneous catalyst, definition of which is required in the rate of reaction as topic. The catalyst is in a different state, different phase as your reactants there. So you need to heat it around 200 or 300 degrees Celsius will have been fine. And that's it really for this 13-mark organic chemistry question. Now question 4, I believe that this is actually the last question in this paper, but we never know. So there are 7 structural isomers. So they have the same molecular formula, but different structural formula. They have 5 carbon, C5H10O. They are carbonyl compounds, so they contain carbon-oxygen double bond. And of course, under the carbonyl compound chemistry, you have learned about aldehydes. If 4 of them are aldehydes, then the rest must be, the other 3 must be ketone. Because, as you know, ketones and aldehydes, they are in the same topic. When they have the same formula, that is because ketone and aldehydes are what you call functional group isomers. And functional group isomers come under the branches of structural isomerism. Now, what is so special about this for aldehyde? Aldehyde A has a straight chain. So, 5 carbon straight chain. They want you to give the structure of each of the 4 isomers. They did not mention about display, skeletal or structural. So that means you can draw either of those displayed, structural or skeletal. Being me, if you have watched my other organic chemistry lecture, you would know that I'm a big proponent of learning about skeletal formula because it's the fastest of all. Doesn't mean that I'm a one-tailed pony. I do know about other formula representation as well. So this is 4 carbon so far. I have 5 carbon. The biggest danger when you draw skeletal formula is you forgot to count. And when you forgot to count, you forgot to check. We don't show the hydrogen bonded to the carbon in a skeletal formula. This is CH3, CH2, 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 CHO. It's a 5 carbon aldehyde. This is what you call pentanal. Now, they are not looking for the name, so you can't give the name. You will not get any mark. They didn't ask you whether it's skeletal or structural. Both of these will have gotten you the mark there. It's a straight chain. This is the simplest aldehyde 5 carbon you can have. 1, 2, 3, 4, 5, C5. And then in terms of hydrogen, 3, 4, 5, 6, 7, 8, 9, 10. And then 1 oxygen. So the molecular formula of these structural isomers will be the same, but they have different structural isomer. Now, B, C, and D are branch isomers, but aldehyde B is the only one that has a chiral center, and therefore you have optical isomers that can rotate plane polarized light in opposite directions. They are mirror images of each other. You cannot superimpose them on each other. The only thing that you can tell apart the difference would be by using plane polarized light that have opposite optical activity. Plane polarized light, something to do with light. That's why the name is called optical, because they rotate the plane polarized light in opposite direction. All their melting, boiling, solubility, whatever other physical properties and chemical properties will be exactly the same. So I'm just going to draw my aldehyde. So this is my CHO group, and then I have a CH3, and then I have a CH2, CH3, and then I have a hydrogen. So I don't show my hydrogen bonded to the carbon. Let me see and count my carbon, and if it's correct, 1, 2, 3, 4, 5. So 5 carbon there. 5 carbon aldehyde because CHO there. And of course, I need to find my longest chain carbon. So 1, 2, 3, 4. But the important carbon is actually the aldehyde. So this cannot be 1. So I have to do 1. And it so happened that 1, 2, 3, 4, that is the longest chain carbon, because 1, 2, 3 versus 1, 2, 3, 4. The 1, 2, 3, 4, 4 carbons, longest chain carbons. So this is what you call butanal. But then this one has a branch. It has a CH3 branch at position 2. This is called 2-methyl butanal. But again, the name is not required in the question. If you give the name, you will not get any mark. They want the structure. So I maintain my structure. I maintain my skeletal formula. And I'll just draw it like that. In fact, you can draw it a bit better than what I've drawn here probably. You can draw it like that. 1, 2, 3, 4. And then at position 2, you have a branch like that. So that would be okay as well rather than this. But I just wanted to show you from this chiral center that I have 1 carbon, 2 carbon, aldehyde carbon, and then a hydrogen there. In terms of the structural formula, follow the structure. Even though this is my important carbon there, so I know it will have CHO at the end. I'm going to start from the 4 there. So perhaps I actually draw it a bit better. Let me just remove that. I will just draw it using this one. And then let me just give you a number, 1, 2, 3, and 4. So this will be CH3, CH2, CH, carbon form 4 bond, 1, 2, 3. There is one hydrogen there. So there is a CH3 in a branch, and then CHO. Structural formula, skeletal formula, both of them are okay. You don't need both of them, you just need one of them. You don't need the name, but then of course you should know how to name them. All right. Now, aldehyde C has 2 methyl group in its structure. D has 3. So 3 what? 3 times CH3. So aldehyde D, I have aldehyde. So I cannot have the methyl there. It must be there. I have 3 methyl. 1, 2, 3. Aldehyde C only has 2 methyl. So 1, 2. Like that. Because this one is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, like that. Am I doing the right stuff? Not really. There are 3 methyl there, so I'm still doing the wrong stuff. This is wrong. Well, I'm sure about D. D is definitely correct. This is 1, 2, and 3. As you could tell, this is propanol, but it's got 2 of that CH3. Both of them is at position 2. So it's 2,2 dimethyl propanol. In terms of the skeletal formula, that is correct. In terms of the structural formula, so CH3 is this carbon here. Carbon from 4 bond, 1, 2, 3, and 4. There is no more hydrogen there. So I'll just draw the branch, CH3, another bracket for the other branch, and then CHO. So both of these skeletal and structural formula, either of them will be acceptable. You don't need the name. I've just done the naming as sort of like practice and recap and stuff. So I still haven't gotten C yet. C has got 2 methyl group in its structure. So based on all of these, what am I doing really? Like that, maybe? Like that. 1, 2, 3, 4, 5. Now this is exactly the same as that. So I don't want that. But I can move my methyl from position 2 to position 3. So I can have like that. So rather than at position 2, I have my methyl at position 3. So what I get is 1, 2, 3, and 4. I get a CH3, CH bracket CH3, CH2, CHO. So follow the thing here. CH3, CH, carbon from 4 bond, there is one hydrogen there. This is the branch in a bracket, CH2, CHO. In terms of naming, you will see that these and these 2, they are what you call position isomer, because I've just moved the methyl group from position 2 to position 3. This is going to be butanol. It's 3 methyl butanol. This is 2 methyl butanol. Position isomers there. Okay. Now draw the 3-dimensional structures for the 2 optical isomers of B. So what I do is I draw the tetrahedral shape first. So make sure you know how to draw the tetrahedral geometry, because you have to show geometry, 3-dimensional. If you don't show the 3-dimensional shape, you're not going to get the full mark for this question. So be very careful there. So give or take around 109.5. Make sure it's not 90 degree. And mirror images of each other. So this is like the imaginary mirror there, and whatever is going from that to that end, so it will be that to that end. So here will be projected onto here. We're looking at isomer number B. So we have a CH2, CH3, a CH3, a hydrogen, and a CHO. The easiest thing I can think about is put the CH2, CH3, the long group, I just put it on top. Some students thought that, okay, I must have mirror image, then they write CH2, CH3. Well, this is a single bond, so you can rotate about freely in a single bond. It wouldn't matter whether you write CH2, CH3, going that way, because you can rotate about the single bond easily, and CH2, CH3 here is the same as that. I know I said mirror image, but that's why I put it on the very top there, because it's very easy to just write this at the very top there, rather than on the other side where it becomes a bit cumbersome. I also have a CH3. So this CH3 is easy to write, so I'll just write it there. I also have a hydrogen. This is probably the easiest one to write. Now actually there's another one which is easier to write, the CHO. The CHO is the aldehyde. So CHO, that's easy to write. So CHO, make sure you go inverted that way. CHO aldehyde, CHO aldehyde. You have one hydrogen. on that carbon. That chiral carbon there has got one hydrogen, it's got a CH3, a CH2CH3, and a CHO. This is your chiral carbon, non-superimposable mirror images, chiral carbon because the carbon is bonded to 4 different groups of atoms there. Okay, for that 2 marks. Now the next bit, describe a chemical test. So this is describe a chemical test. You need to distinguish, you need to tell apart the difference. My handwriting is pretty bad there. So tell apart between any of the 4 isomers A to D and any of the other 3 structural isomers. So these must be ketones, which I mentioned, because A to D, they are aldehydes. So a chemical test, so that is 1. And in your answer, you should describe any reagents and conditions, as well as explaining what you will see in each case. Well, the simplest reagent I can think of is add 2,4-dinitrophenyl hydrazine. Some students are petrified by this spelling here because it looks really long. But if you have done some A2 benzene chemistry, you know this is a phenyl, and then you have hydrazine. So hydrazine is basically NH2NH2, where you replace one of the H with a phenyl. And then you have a nitro, which is NO2, at position 2, as well as position 4. You get 2,4-DNPH. And when you add it with A to D, which is aldehyde, and also ketones, and I am wrong because both of them, this will give you orange PPT, orange precipitate. This will also give you orange PPT. So this is a wrong test because they want to tell apart. So this is not suitable at all. I am not going to use that. So I've just wasted my time. I've just wasted your time, but no worries because you can see the positive result for both aldehyde and ketones. They're not going to tell you apart the difference. So what do we need then? We need to use Tollens. Tollens reagent or Fehling's reagent, that is a specific test for aldehyde. So Tollens reagent is colorless. It basically contains silver with 2 ammonia. This is a plus there. And this is aqueous, colorless. And you will get a silver mirror forming. A silver mirror will form for the aldehyde as the silver plus 1 get reduced to silver 0, and the aldehyde will get oxidized. Whereas for the ketones, you will get, solution remain colorless. The solution remains colorless because your Tollens reagent is basically colorless to begin with. So I'm going to remove that 2,4-DNPH thing because that was obviously wrong concept, wrong chemistry. I don't want to be teaching wrong chemistry to you, so hopefully you will forgive me there. Alright, so there is actually another choices. So use Tollens reagent and heat. You need to heat gently as well, so there's the conditions. Or you can use the other one, use Fehling's reagent. So Fehling's reagent is more like Benedict's solution that you use to test for reducing sugar, but we don't call it Benedict's solution in chemistry. Instead, we know that it contains some sort of copper 2 plus aqueous plus something, and you need to heat it. That's part of the conditions. So what you get then with the aldehyde is you will get a red-brown precipitate, a red-brown solid, which is copper 1 oxide, copper plus 1. You need 2 of them to balance out the charge of the oxygen. And you get that with aldehyde because it can be oxidized. But then here, with ketones, the solution remains blue. So they say, describe a chemical test. How can you tell apart? You should describe any reagent condition, explaining what you would see. So in terms of explanations, aldehyde can be oxidized further. Aldehydes can be oxidized further. Ketones cannot. Ketones cannot, or ketones can't be oxidized further. Ketones can't be oxidized further. Hopefully that makes sense to you. That is in terms of explanation. And in terms of the observation, I have listed one for Tollens and one for Fehling's. In reality, you just need one chemical test. So it's or either or of these, but the observation remains very important. People thought that everything is just colorless, but when you just contain copper 2 plus, that's just going to remain blue without any redox reaction happening. That is colorless solution. It just remains colorless without any redox happening. Here, there is some sort of redox happening. Copper plus 2 become copper plus 1, silver plus 1 becomes silver 0 as the aldehyde get oxidized in both cases by both of these reagent there. Anyway, remember what I said earlier about the 2,4-DNPH? Now a test that will give the same result with all of them. So basically they have ketones or aldehyde. They have the CO carbonyl group. So add 2,4-dinitrophenylhydrazine. So just to remind yourself that what does it look like? Well, hydrazine is NH2NH2. They use it as a rocket fuel. I'm going to remove one of the hydrogen and then change it with a benzene ring. And then I have a NO2 at position 2 and also at position 4. So that is 2,4-dinitrophenylhydrazine. That is the test. Now the observations is all 7 isomers, all 7 structural isomers will form or will give an orange PPT. Whoop, hang on, you cannot write PPT in a theory paper because they're not in practical paper. You can say form orange crystals or orange precipitate. That is going to be positive because you have the CO aldehydes and ketones, and you can only tell them apart if you use toluenes or phthalings. They are very specific to the oxidation of aldehyde, which ketones cannot be oxidized further. But when you do those reactions with aldehydes or ketones, you are not exactly doing redox chemistry. Let me just show you one with the ketone. So for instance, if I have that ketone, what actually happened is you get a condensation reaction. This is as stated in the Cambridge syllabus, condensation reaction. And a Cambridge endorsed textbook will show you what actually happened there. You will lose the H there. You will lose the O there. You will also lose this H there. So what actually happened is, well, the rest of the molecule doesn't change that much. I'm going to copy paste that. I'm going to lose the 2 hydrogen. And now it is going to be bonded in place of the carbonyl. Instead of the oxygen, it's now double bond to the carbon there. And I have R and R dash, and I get water. Condensation reaction, the 2 molecules come together and kick out a small molecule. In this case, it kick out water. If this is H there, meaning CHO aldehyde, then you just get one of them being H and one of them being the alkyl group. Okay, that's the end of the 11 mark questions, the end of this paper as well. So thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And all these yearly paper tutorials, the full yearly paper tutorials, they're only available to the silver tier members on my channel. So it doesn't cost that much. Buy me a cup of coffee, will you? And continue supporting my work on the channel and share the channels and share news about these tiered membership with your friends, your chat group, your juniors, seniors, and other people you think this membership would benefit. Okay, see you in the next tutorial video. Thank you for watching again.